Today, in this explainer, we aren't looking at giant concrete cooling towers or massive engineering feats. We are zooming way, way in. We're going to explore the fundamental subatomic physics that literally allow us to control nuclear power. Think about this for a second. Before we can even begin to optimize a modern nuclear reactor, we have to solve a pretty extreme physics problem. Fission spits out neutrons at absolute blistering speeds. We're talking millions of miles an hour. And if we want to maintain a safe, official chain reaction, we have to somehow put the brakes on them. But how on earth do you slow down something that tiny moving that fast? Well, the source text gives us this brilliant little visual to help us out. It says the process is akin to the collision between two billiard balls. And honestly, that's the perfect way to think about it. Controlling a reactor all comes down to the microscopic, precise kinematics of how these tiny particles bounce off of one another. Section 1, the setup, neutron scattering. Let's look at the baseline rules for our main players on this subatomic pool table. Now, in reactor physics, these microscopic bounces are officially called neutron scattering. And the ground rules here are actually super strict. A neutron flies in, hits a target nucleus, and a neutron bounces off. That's it. The target doesn't magically transmute into a totally different element, and the neutron doesn't just vanish. The product is the exact same as the target, and what flies out is the exact same as what went in. The only real currency being exchanged here is kinetic energy. They hit, they bounce, and the kinetic energy completely shifts hands. So, rule number 1, elastic bounces. Let's see what happens when that energy is perfectly conserved. I want you to picture a perfectly executed break on a pool table. You know, the cue ball slams into the stationary pack. Smack! The pack scatters, gaining energy and flying across the felt, while your cue ball violently slows down. But here is the kicker. If you were to somehow add up all of that movement, the total kinetic energy before the hit and after the hit stays exactly the same. It's just been shared. That is elastic scattering in a nutshell. The stationary nucleus takes the hit, gains energy, and starts moving, while the incoming neutron slows down. And as we can see here, this elastic bounce actually happens in two distinct ways. On the left side of the visual, it's super straightforward. It's a direct reaction. The neutron just smacks the nucleus and ricochets off. Simple, right? But check out the right side. This is wild. The target actually captures the neutron for a split second, forming this unstable compound nucleus with a little extra mass before immediately spitting a neutron right back out. But in both scenarios, the total kinetic energy remains completely conserved. The math balances perfectly. But what happens when the math doesn't perfectly balance? That brings us to rule number 2, inelastic bounces. Okay, inelastic scattering is not just a simple ricochet. It's a bit more of a multi-step dance. Just like we saw a moment ago, the target grabs that incoming neutron, creating a temporary complex nucleus. It eventually releases a neutron, sure, but here is the big catch. It leaves that residual nucleus behind in a highly excited state. It's vibrating, it's energetic, and to calm back down to its normal ground state, it has to vent that energy. And it does this by firing off gamma radiation. If you look at the far right of this visual, see that little squiggly line? Yeah, that is our gamma ray. Because the nucleus had to basically spend energy to calm down, there's a net reduction in the total kinetic energy of the whole system. The equation isn't perfectly balanced anymore. Some of that kinetic energy was literally stolen and converted straight into gamma radiation. Now, creating that excited state isn't free. It takes a very specific amount of energy. So for an inelastic bounce to even happen, the incoming neutron has to hit with a minimum amount of force, which is called the threshold energy. And this threshold is entirely dictated by the target's mass, which we call Bay, and the reaction's negative Q value. Long story short, if the neutron doesn't hit hard enough to meet that threshold, an inelastic bounce simply cannot happen. The weight class, the math of the bounce. Let's dig into the numbers and see how the mass of that target nucleus, A, really starts dictating how we design reactors. Remember, our whole goal here is to slam the brakes on these super fast neutrons, right? We want them to lose as much energy as possible with every single collision. The formula for maximum energy lost tells us that the energy stripped from the neutron completely depends on a variable called alpha. And if you look closely at that alpha equation, it's calculated using the mass of our target nucleus relative to a neutron. It's A-1 over A+1 squared. So here is the absolute crucial point. What happens to that equation if our target mass A is exactly 1? Well, 1 minus 1 is 0.
alpha becomes zero. And if alpha is zero, our maximum energy loss equation just becomes E, the total incoming energy. Think about what that means. If a neutron hits a lightweight nucleus that weighs almost exactly the same as it does, it loses almost its entire energy in one single devastating hit.
The grand finale, moderation. Let's zoom out and see how this very specific math lets us tame an entire nuclear reactor. If the math tells us we want a target mass A as close to 1 as humanly possible, where do we look? Hydrogen. Because its mass is nearly identical to a neutron, hydrogen is the ultimate subatomic bumper. If a neutron hits a really heavy nucleus, it just ricochets off, like bouncing a ping pong ball against a bowling ball. It barely slows down. But if it hits hydrogen, it's like a cue ball perfectly striking another cue ball. It transfers almost all of its kinetic energy and stops the neutron dead in its tracks. To really wrap your head around how efficient this is, think about the number 20. It is absolutely astounding, but it takes fewer than 20 collisions with light nuclides like hydrogen to slow a neutron down from a few million electron volts, which is just a chaotic, blistering speed, to a mere fraction of a single electron volt. Less than 20 bounces, and the beast is totally tamed. And this really ties the whole explainer together. This is exactly why low-energy thermal reactors rely entirely on light nuclides like hydrogen or carbon to act as moderators. They use that high elastic scattering to hit the brakes incredibly efficiently. Heavy nuclides, on the other hand, don't absorb energy well elastically at all, so they rely way more on inelastic scattering, where those tricky threshold energies come into play. It is literally a totally different physical game depending on the weight class of your pull table. It's honestly kind of incredible to think about. Our massive energy grids, our modern industrial power, all of it relies on mastering this invisible, microscopic game of pool. It really leaves you wondering, as we push toward next-generation reactors and entirely new fuels, how will manipulating these exact same subatomic bounces unlock the future of global energy?